Okay, hi everyone. Back for more CS224N. Okay, so for today, the plan is essentially a continuation of what we started on Tuesday. So I'm going to say more about language models and more about RNNs, in particular introducing a more advanced form of recurrent neural network, which was for a while very dominant. LSTMs, we'll talk about those. And then in the latter part, as something to be done with recurrent neural networks, we'll start looking at neural machine translation. Okay, so on Tuesday, what we did was we introduced language models, a system that predicts the next word, and then I introduced recurrent neural networks. So that was this new neural architecture that can take sequential input of any length, and it applied the same weights at each step and can optionally produce output on each step. So these are two distinct notions, though they tend to go together. So recurrent neural network can be used for other purposes on any kinds of sequence, and I'll mention a few of those later today. And language modeling is a traditional component of many NLP tasks, anything to do with generating text or estimating likelihoods of pieces of text, and indeed in the modern instantiation of large language models, essentially everything we do in NLP is being done by language models. So a language model, one way to do it is with the recurrent neural network. It's certainly not the only way. We also talked last time about n-gram language models, which were language models, and then starting next week we'll start to talk about transformers, which are now the most widespread way that's used for building language models. So just finish off a teeny bit that I didn't get to last time on evaluating language models. Well, one way to evaluate language models is what I did in class last time, generate some text and say, hey, doesn't this text look good? But you know, often we want something more rigorous than that. And the standard way to evaluate language models is to say, well, you know, a language model scores a piece of text and says how likely it is. And our standard for text in a language is stuff produced by human beings. So if we find a new piece of text, which wasn't text that the model was trained on, right? We want some fresh evaluation data, and we show it to a language model. We can then ask the language model to predict the successive words of this text. And the better it is at doing that, the better a language model it is, because it's more accurately able to predict a human-written piece of text. And so the standard way that that is measured is with this measure that's called perplexity. And so for perplexity, we are taking the probability of a prediction from the language model, we're inverting it. So instead of it being, you know, 0.002 or something, we're turning into 500 or something like that. And then we're taking those numbers, we're taking the product of them at each position in the text, and then we're finding the geometric average of them. So that's the measure that's normally used. But if in this class, we've been tending to look at negative log likelihoods and the idea of cross entropy. And so what perplexity is it's just the exponential of the cross entropy. So if you're already familiar with negative log per word, negative log likelihoods, if you just exponentiate that, you then get the perplexity. Now there's one other little trick as to what base you use for your logarithms and exponentials. I mean, traditionally thinking of sort of binary and stuff, a lot of the time people use base 2 for measuring perplexity. That's kind of gone out now. A lot of the time now people are using natural logs, but if you're comparing perplexity numbers, they're going to be different depending on what base you're using for things, so you need to be aware of this. So from a sort of a modern perspective, it kind of makes no sense why perplexity is used. The story of why perplexity was used was, in the bad old days of symbolic artificial intelligence, when all of those famous people like John McCarthy and Ed Feigenbaum were around doing logical-based systems, some people then essentially at IBM, including Fred Jelinek, started exploring probabilistic methods for speech recognition and other similar methods. The story Fred Jelinek used to tell was, well, at that time, this was in the late 70s or early 80s, that none of the AI people that he was trying to talk to understood how to do any real math and didn't understand any information theory notions of doing things like cross-entropy or cross-entropy rate. So he had to come up with something simpler they could understand. And so what he came up with is by sort of doing this exponentiated perplexity, you can think of a perplexity number as being equivalent to how many uniform choices you're choosing between. So if the perplexity of something is 64, that's like having a 64-sided dice that you're rolling at each time, and that's your chance of getting a 1 on that is your chance of guessing the right word. So that was why perplexity got introduced, but it's kind of stuck, and so when you see scores for language models, you generally still see perplexities. So a lower perplexity is better. So here are the kind of numbers and where progress was made with neural language models. So before that, people used n-gram language models, and people used clever ways to smooth them using methods I vaguely alluded to last time of this add case smoothing and doing back off. Actually, people use cleverer methods around the 2000s decade. The cleverest method known of smoothing n-gram language models was this thing called interpolated Kneser-Nye smoothing. And so for a big language model using that, the perplexity was about 67. Which in some sense means that you weren't very good at predicting the next word. But that had actually been enormous progress. When I was a young person doing NLP, perplexities were 3-figure numbers, right? You were commonly seeing, perplexities of 150 or something like that. So progress was made. So when RNNs were first introduced, people weren't really actually able to do better with a sort of a pure RNN, but they could do better by combining an RNN with something else, such as a symbolic maximum entropy model, which I'm not going to explain, but those are numbers like that 51. But where progress really started to be made was when LSTM started to be used as an improved RNN, which is what I'm going to come to next. So here are some LSTM models, and now you're getting numbers like 43 and 30, and so for 30 you've sort of halved the perplexity, which in cross-entropy terms means you've reduced the cross-entropy by about 1 bit. And so you've made real progress in your language modeling. Now, by modern standards, these numbers are still really high, right? For the best language models that we have now, you're getting perplexities in the single digits. You're getting models that are very often able to guess exactly the right word, though of course not always, because no one can predict what word's going to be said by someone next in a lot of circumstances. Okay, so to motivate LSTMs, then wanted to sort of say a bit about how there were problems with RNNs and why that motivated fixing things. And these are the problems of vanishing and exploding gradients. So what we wanted to do was say, okay, we've tried to predict a word at position 4, and often we're going to get it, we're not going to predict it with 100% probability, so we have a loss that's a negative log likelihood we give to that word, and we're going to want to backpropagate that loss through the sequence and work out our gradients as we always do. Now, just one note about something someone asked me after class last time. You know, I sort of showed it backpropagating the whole sequence, but we're doing this at every time step, right? So we're going to backpropagate a loss from time step 2, backpropagate a loss from time step 3, 4, 5, 6, 7. We're doing it for each one, and in one of the slides last time we then discussed how we're going to sum all of those losses or work out the average loss. But for doing this one, when we backpropagate this loss, what happens? Well, what happens is we're going to do the same kind of chain rule where we're multiplying these partial derivatives at every time step. And well, here we've only got a few of them, but you know, maybe we're going to have a sequence 30 long, and so we're going to be multiplying each time the partial of hk with respect to the partial of hk minus 1. And so what kind of effect is that going to have? In particular, you know, we might ask, what happens if these are small, or what happens if these are large? Well, if they're small, the gradient will gradually get smaller and smaller and disappear as we backpropagate it along the sequence. Yeah?
Chris, so why we're taking partial j over partial h? Should we take partial j with respect to w?
Sure. I mean, we're doing that as well, but you know, in general, we have to walk the partials along, and then you know, we then have a w at the next step. I mean, if we're thinking of the sort of computation graph that we're sort of doing the chain rule backwards along, we're going to be going through a w at each step and then arriving at another h, right? Yeah. So, I mean, at this point, you can do some math and thinking about things. And there's a couple of papers that are mentioned at the bottom here, which I'm actually rushing ahead, not going to do very carefully. But the point is that if you're taking the partial of ht with respect to ht minus 1, and if you make a simplifying assumption and say, suppose there isn't a nonlinearity, suppose sigma is just the identity, then what the partial will be is the matrix WH. And so if you keep on backpropagating along the recurrent neural network, what you're going to be doing is ending up with powers of the matrix WH. And then there's the question of what happens when you raise that matrix to higher and higher powers. Well, at that point, you can represent the matrix in terms of its eigenvectors and eigenvalues. And then there are two possibilities. Either all the eigenvalues are less than 1, and that means that that number will be getting smaller and smaller as you raise it to higher power. Or it can have eigenvalues that are larger than 1, and then things will get bigger and bigger as you go further back. So essentially, as you backpropagate the gradients backwards, unless things are sort of just precisely corresponding to a largest eigenvector of largest eigenvalue of approximately 1, you're either going to get a vanishing or an explosion, and both of those will be kind of bad. So why is vanishing gradient a problem? I mean, in a sense, you could think it's not a problem. It's what should be happening, because all else being equal, you know, the closest words are the most relevant ones, and so that's where you should be updating your parameters the most. And to some extent that's true, but nevertheless, this vanishing gradient in this model happens much too severely, so that if you're looking at the loss from a later position and comparing it to the loss from an earlier position, and then you're seeing how things are updating. It's sort of primarily the update is being determined by the very nearby loss and not by the far away loss. That the gradient signal from far away is much, much smaller. And, well, that's bad because, you know, overall for language modeling, there are lots of cases where we want to be able to transmit signals a long distance. So here's my piece of text. When she tried to print her ticket, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her. Yeah, so, you know, to a human being, you know, it's obvious we can predict this with pretty much probability 1, you know, so really low perplexity for making this decision. But, you know, that depends on getting back to the tickets, which are sort of about 20 odd words back, right? If you're just seeing installing the toner into the printer, she finally printed her, could be anything. It could be her paper, her invitation, her novel, lots of things it could be. You're certainly not going to guess tickets. So we sort of want to have these really long distance dependencies, but we're only going to be able to learn these long distance dependencies if we're actually getting sufficient signal between that position and when the word tickets appears near the beginning, that we can learn the fact that having that tickets 20 words back is the good predictive thing for predicting tickets here. And what we find is that, you know, when the gradient becomes very small, the RNN doesn't learn these kind of long distance dependencies, and so it's unable to sort of make these predictions well at test time. I mean, this is a very sort of just rough back of the envelope estimate, but, you know, what people actually found is that, you know, with the kind of simple RNN that we've introduced up until now, that the amount of effective conditioning you could get was about 7 tokens back. That if things were further back than that, it just never learnt to condition on them. And so, you know, compared to when we were talking about n-grams, and I said, usually the maximum people did was 5 grams, occasionally a bit bigger, because of the fact that there was this exponential blowout. Although in theory, we've now got a much better solution. In practice, because of vanishing gradients, well, we're only kind of getting the equivalent of 8 grams, so we haven't made that much progress, it feels like. So there's a reverse problem which can also happen of exploding gradients. So if the gradient becomes very large because the eigenvalues of that matrix are large, well, what we're doing for the parameter update is, you know, we've got a learning rate, but essentially if the gradient is very large, we're going to make a very, very large parameter update. And that can cause very bad updates because, you know, we're sort of assuming that we're taking a step in the direction of the gradient, and, well, we might overshoot a little, but we'll be roughly in the right zone. But, you know, if we had an enormously exploded gradient, well, we could kind of be sort of walking off anywhere, and, you know, we think we're heading to the Sierras and we end up in Iowa or something like that, right? You know, that we could just go arbitrarily far, and where we're ending up, it might not be making any progress whatsoever. So exploding gradients are a problem. They can also cause infinities and nans, and they're always a problem when you're training models. Now for dealing with exploding gradients, this is the accepted wisdom. This unfortunately this isn't highfalutin math, really. What people use for exploding gradients is a crude hack. They clip gradients. But, you know, it works really well, and you really want to know about this because clipping gradients is often essential to having neural networks not having problems. So what we do for gradient clipping is we work out the norm of the gradient, and if it seems too large, and that varies, but that's normally 5, 10, 20, something like that for a norm of a gradient is seen as the limit of what's okay. If the norm of your gradient is too large, you just scale it down in every direction and you apply a smaller gradient update. It works. So that problem is solvable, but fixing the vanishing gradient seemed a more difficult problem, right? That this was the problem that our RNNs effectively couldn't preserve information over many time steps. What seemed to be the problem there? The problem seems to be really that we've got sort of an architecture that makes it very hard to preserve information. So if we look at sort of the hidden state from one time step to the next time step, it's completely being rewritten, right? So we're taking the previous time step's hidden vector, we're multiplying it by a matrix which completely changes it in general, adding in other stuff from the input. So if we just like to say, we'd like you to carry forward information, there's useful stuff in HT-1, can you just kind of keep it around for a while? It's not actually very easy to do in this formulation because, trying to learn W vectors that will mostly preserve what was there before isn't at all an obvious thing to do. So the question was, could we design an RNN which had a sort of a memory where it was easy to preserve information? Yes?
So in one of the earlier slides, you mentioned the exponentiation happened. During their analysis, they removed the nonlinearity.
Yeah.
So we're having a nonlinearity and sort of doing the differentiation to prevent vanishing or exploding?
No, it actually doesn't. I mean, you can make an argument that it should help because you've got, effectively, if you've got something like tan H, you've got a flattening function. So it should help somewhat, but it doesn't solve it, even if you're using a tan H nonlinearity. Well, so I guess it should help with exploding, though. Actually, even that still happens, but it definitely doesn't help with the vanishing.
Because if you have a sigmoid, then I think the partial of that is 1 minus the sigmoid value. So you're always pushing the value between 0 and 1. So it's not going up or going down, it's staying between 0 and 1. But so, yeah.
0 into sigmoid.
Well, I guess, wouldn't it go up and down between the layers then? So if you have a really small value, that becomes 1 minus a really small value.
It's sigmoid times 1 minus sigmoid.
Oh, it's sigmoid times 1 minus sigmoid. Okay, that still vanishes. Okay.
Yeah, so can we have a different architecture so we have a memory that you can add to? And so that led into this new kind of neural network, the LSTM. So this is going back a few years. But at any rate, this was trying to improve series suggestions, and the big breakthrough that they were being described was, we're now using an LSTM in the keyboard prediction, and the whole advantage of that was it was going to be able to predict context further back, so you could differentiate between the children are playing in the park versus the Orioles are playing in the playoff. Okay, so the sort of big thing that was seen as very successful was these LSTMs, long short-term memory. Just to say a little bit of the history here, right? Just on how to parse this name, right? That I think people often don't even understand it, right? So what you were wanting to do was model short-term memory, right? Because so for humans, people normally distinguish between the short-term memory of stuff that you heard recently versus things that you permanently stored away. And the suggestion was, well, in short-term memory, humans can remember stuff for quite a while, right? If you're having a conversation, you can still remember the thing that the person said a few turns ago in the conversation. So bring back up of, oh, didn't you say they took last weekend off or something, right? And well, the problem was that the simple RNNs, their short-term memory was only about 7 tokens, and so we'd like to make it better than that, and so we wanted long short-term memory, and that's where this name came about. And so this was a type of recurrent neural network that was proposed by Hochreiter and Schmidhuber in 1997 as a solution to the problem. I mean, there's actually a second relevant piece of work that came a few years later that, that first paper is the one that everybody cites, but there's then a second paper by Gers and Schmidhuber in 2000, which actually introduces a crucial part of the LSTM as we've used in the 21st century that wasn't in the original paper. So there's sort of an interesting story of all of this. So, that Jürgen Schmidhuber and his students did a lot of really crucial foundational work in neural networks in the sort of these years, in the later years of the 90s, when just about everybody else had given up on neural networks. So unlike these days where, doing pioneering work in neural networks is a really good way to get yourself hugely compensated jobs at Google, Meta, or OpenAI, it really wasn't actually in these days. So, if you ask, gee, what happened to these students of Hochreiter and Gers, that both of them are still in academia, but Gers seemed to give up on AI and neural networks altogether and does stuff in the area of multimedia. And Sepp Hochreiter is still in machine learning, but for quite a long time he sort of basically gave up on doing more general neural network stuff and went into bioinformatics. So if you look at his publications from about 2000, 2015, they were all in bioinformatics, and most of them weren't using neural networks at all. Though kind of nicely, I mean, he's actually gotten back into neural networks more recently and is publishing in neural networks again. So really not much attention was paid to this work at the time, and so it only sort of really kind of gradually seeped out further. Schmidhuber had a later student in the mid-2000s decade, Alex Graves, and Alex Graves did more stuff with LSTMs, and for people who've seen speech recognition where people commonly do CTC loss and decoding, Alex Graves invented that. But most crucially, Alex Graves then went to Toronto to be a postdoc for Jeff Hinton, and that sort of brought more attention to the fact that LSTMs were a good model. And then Jeff Hinton went to Google in 2013, and that was then sort of the use of LSTMs at Google in the sort of 2014 to 16 period was when they really sort of hit the world and became for a while the completely dominant framework people use for neural networks. In the world of I guess startups, this is what you call being too early for the first people. Okay, long short-term memories, back to the science. Let's see. There's a slide here that talks about long short-term memories, but maybe I'll just sort of skip straight ahead and start to show the pictures. So we've still got a sequence of inputs, xt, and the difference now is inside our neural network, we're going to have two hidden things. One that's still called the hidden state, and the other one that's referred to as the cell state. And so what we're going to do is we're going to modulate how these things get updated by introducing the idea of gates. And so gates calculated things, vectors, whose values are probabilities between 0 and 1, and they're things that we're going to use to sort of turn things on or shut them off in a probabilistic way. So we're going to control the movement of information by having gating. And so we're going to calculate 3 gating vectors. So these vectors are the same length as our hidden states. And so the way we calculate these gating vectors is with an equation that looks basically exactly the same as what we were using for recurrent neural networks. Apart from the sigma there is definitely going to be the logistic that goes between 0 and 1, so we get probabilities. And the 3 gates we're going to calculate is a forget gate, which is going to say how much do we remember of the previous time's hidden state. I think the forget gate was actually wrongly named. I think it makes more sense to think of it as a remember gate because it's actually calculating how much you're remembering. Okay, then we've got an input gate, and the input gate is going to say how much are you going to pay attention to the next input, the next xi, and put it into your hidden state. And then you have an output gate, and the output gate's going to control how much of what's in the cell, which is your primary memory, are you going to transfer over to the hidden state of the network. Okay, so once we have those gates, what we're then going to do is have these equations, which are how we're going to sort of update things. So the first thing we're going to do is work out a potential new cell content. So the new cell content is going to be calculated exactly using exactly the same kind of equation we saw last time for recurrent neural networks. We're going to have these 2 matrices, the cell W and the cell U, and we're going to multiply one by the last time's hidden state and the other by the new input, add on a bias. And that's a potential update to the cell. But then how we're actually going to update the cell is by making use of our gates. So we're going to say the new cell's content is going to be the old cell's content Hadamard producted with the forget gate. So that's how much to remember of the previous cell's content, plus this calculated update Hadamard producted with the input gate, how much to pay attention to this new potential update that we've invented. And then for calculating the new hidden state, that's going to be the Hadamard product between the output gate and our CT having been put through a TAN-H. And, you know, one idea here is, you know, we're thinking about how much to keep on remembering what we've had in the past. But, you know, for thinking about sort of only sending some information to the hidden state, sort of a way to start thinking about that is, you know, the hidden state of a recurrent neural network is sort of doing multiple duty, right? Like, on one part of it is we were going to feed it into the output to predict the next token. But in another thing it's going to do is we just want it to store information about the past that might come in useful later and that we'd like to kind of have carried through the sequence. And so really only some of what's in the hidden state we want to be using to predict the current word. Some of it isn't relevant to predicting the current word, but would be good stuff to know for the future, right? So, you know, if the previous words were sat in, for predicting the next word, we basically just need to know we're in a sat-in context where the or will come next. But, you know, if earlier on the sentence had been saying the King of Prussia, somewhere in the hidden state, we want to be keeping the information that there's a King of Prussia because that might be relevant for predicting future words. And so it makes sense that we only want to have some of what's in our memory being used to predict the the next word in the current context. So the cell is our long short-term memory, and then we're moving over to the hidden state, things that are going to be relevant for generation. Yeah, I've sort of said that. Okay. All these are vectors of the same length n. Yeah, so all of these things, both the gates and the new values for the cell and hidden state, they're all vectors of length n. And part of how things actually get convenient when you're actually running of these is up until here, all of these things have exactly the same shape, so you can actually put them all together into a big matrix and do the computations of all 4 of these in terms of one big matrix if you want. Question?
If you did not have the vanish activation in the hidden state update, then the output gates should have been expressed by both the input gates and the forget gate, right?
You're saying if this bit wasn't here,
Right.
then
you would not need an output gate,
well,
because FT and IT would have been able to express it, account for it in some sense. My question is, how much does having...
no, wait. Well, no. To the extent that you want to mask out part of what's in the cell so it's not visible when you're generating the next token, isn't it still useful to have an output gate?
You can essentially have HT is equal to CT, right? If you don't have vanish.
But you don't want HT equal to CT. You want some of the contents of CT to be masked out, so you're not seeing it when generating the output.
But that masking would have been accounted for by FT and IT, is my...
No, because you want to keep it in CT. There's information you want to keep in CT for the future, but you don't want visible when generating the current next word. Yeah. In some sense, the bit I have the hardest part explaining is why is it necessarily better to have a tan H here? I mean, you can sort of argue that it's a way of this can just stay unbounded real numbers, and then this is getting it back in the shape of stays between 0 and 1, which is good for the hidden state, but it's a little bit, I guess they did it that way and it seemed to work well. Okay, here's another way of looking at it, which may or may not be more helpful as a picture. So, at each time step, we've got, as before, an input, a hidden state, and then we're going to calculate an output from that hidden state. But we've sort of got this more complex computational unit, and these pictures of this more complex computational unit were diagrams that were made by Chris Olah, who's someone who now works at Anthropic. And so if you blow up in that, this is sort of showing the computation. So you're sort of feeding along recurrently the C cell as the primary recurrent unit, but you've also got carried along H, because H is being used to calculate stuff for the next time step, and then a new H is being generated. And so you're computing the forget gate, you're forgetting some of the cell content, you're computing an input gate, you're using that to compute a potential new cell content. You write some of that into the cell depending on the input gate. Then you compute an output gate, and then some of the cell will go into the computation of H depending on the output gate. And then just like for the previous recurrent neural network, for working out what the predicted next word is, you're working out an output layer by taking the H and doing another matrix UH plus B2, and then using a softmax on that to actually predict the next word. Okay, so, this all seems very complex. And, back in, do you have a question? Yeah.
Sorry, I just have a quick question. So how are we deciding the threshold? I imagine it's just some sort of threshold around the probability of like what we're remembering and what we're forgetting?
So we're getting more than a threshold, right? Because we're calculating a whole vector of forgetting and remembering. So therefore, it can choose to say, okay, dimensions 1 to 17, keep all of that, and throw away dimensions 18 to 22, or really probabilistically to different extents. And so it's sort of unspecified. It's up to it what it learns, but we're hoping that it will learn that certain kinds of information is useful to keep carrying forward for at least a while, but then we can use both the contents of the hidden state in the cell, of the next input to decide to throw away certain information. So we might think that there are certain cues. For example, if it sees the word next, it might think, okay, change of topic, now would be a good time to forget more stuff and reset. But it's sort of learning which dimensions of this vector to hold around in an unconstrained way, whatever's useful to do a better job at language modeling. Okay, so this all looks like a very complex and cantankerous design. And, quite honestly, when teaching this around 2016, 17, and this was the best kind of neural network we had for language modeling. We literally, spent hours of class time going through LSTMs and variants of LSTMs with different properties, because, there are different ways you can do the gating. You can have less gates or more gates and do different things. And it seemed the most important thing to know. In 2024, it's probably not the most important thing to know, but on LSTMs are a thing to be aware of. We are going to use them for the assignment 3, but you can just ask PyTorch for an LSTM and it'll give you one that does all of this stuff. But there is one thing that I really want to sort of focus on as to what is the good thing that an LSTM achieves? And really the secret for why you get this fundamentally different behavior in an LSTM is you have that plus sign right there, right? That for the simple recurrent neural network, at each time the next hidden state was a result of multiplicative stuff, and therefore it was very hard just to preserve information. Whereas the essence of the LSTM is to say, well, look, you've got this past memory of stuff you've already seen, and what we want to do is add some new information to it, which fundamentally seems like kind of right for human memories, that they're sort of basically additive. And when I said actually it was the second Gers paper that introduced a crucial part of the LSTM, the first version of the LSTM didn't have the forget gate. So it was a purely additive mechanism that you were deciding what to add to your memory as you went along. But that proved to be not quite perfect, because if you keep on adding more and more stuff over a long sequence, that tends to be dysfunctional after a certain point. And so the big improvement was then to add this forget gate, so some of it went away. But nevertheless, having things basically additive fixes the problem of gradient flow. You no longer have vanishing gradients, and it makes it something that seems much more memory-like. You're adding to the things that you know. Okay, so the LSTM architecture allows you to preserve information over many time sets in the cell, right? So if you set the forget gate to 1 and the input gate to 0, you're just linearly passing along in the cell indefinitely the same information. Okay, it's not the only way that you can do long-distance information flow, and we're going to look increasingly in future lectures at other ways you can do long-distance information flow. And just to sort of give a bit of a peek about those now and to think about other architectures, but there's a question. No? No question. Yes.
So since you're mentioning that the plus like handle the shift and vanish gradient, Does it help with exploding gradient at all? Does it make it worse? Is there like no difference? Or?
No, it also helps with exploding gradients because of the fact that you're not doing this sequence of multiplies all the time, that you sort of have this addition operator. So one thing you could wonder is vanishing and exploding gradients just a recurrent neural network problem? And it's not. I mean, it occurs earlier and worse when you've got long sequences. But if you start building a very deep neural network, surely the same thing is happening. You know, the parameters aren't the same, so it's not quite just raising one matrix to a power, but surely, depending on your matrices, you tend to have the same problem that either your gradients are disappearing or else they're exploding. And that's what people found, and that was part of the reason why in the early days people weren't very successful building deep neural networks, was because they suffered from problems of this sort, that if you had basically vanishing gradients in a deep neural network, you got very little gradient signal in the lower layers, therefore their parameters didn't really update, therefore your model didn't learn anything in the lower layers, therefore the network didn't work well. And you know, that was part of why things were stuck in the days around the early 2000s of deep networks didn't work. And so there are other ways you can think about fixing that. So one common way of fixing it is to add more direct connections. So, you know, the problem when we went through our recurrent step was we were sort of had this in-between stuff of doing a matrix multiply and blah, 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 blah. And that kind of caused indirectness and the possibility for things to either explode or vanish. So this network is written sort of upside down when I stole the picture from the paper, so we'll just have to deal with that. Right, so we're going downwards from here to the next layer. So, you know, rather than going through sort of weight layers and weight layers, which will start to produce the same kind of problems, what you can do is sort of apply the same trick in a vertical network and say, well, look, I can also just carry the input around with an identity function and add it on here. And so then I've got this sort of direct carrying of information. And so that led to the residual network, which was what completely transformed computer vision models and made them much more learnable than pure networks that lack these residual connections. If you sort of start heading down that path, you can think, well, why only provide these residual loops that take you one step? Maybe I could directly connect each layer to all the successive layers. And so people played with that idea, and that led to the so-called dense net, where you have these kind of skip connections linking to every other layer. A variant of the residual network, the ResNet, which was actually again introduced by Schmidhuber and students, was to say, well, rather than just directly adding in the input summed with the output of the neural network layer, maybe again we'd be better off having gating so that you are deciding via gates how much of the input to have skip around. And so that led to a variant, the highway net, where you've got sort of gated residual networks. So various ideas of doing that. Not going to say more about that right now. I want to skip ahead and sort of do the rest of neural nets and get on to machine translation. Okay, so once you have RNNs, where RNNs is including LSTMs, normally in practice LSTMs, you can use them for anything else where you're doing sequences. And so there are lots of places they're used in NLP. So if you want to assign words parts of speech, like nouns and verbs, that would be commonly done with a part of speech tagging LSTM. If you want to be assigning named entity labels like location, right? I did this toy version where we were assigning a label to the middle of a window, but if you wanted to assign a label at each position, you can use an LSTM for named entity recognition. You can use an RNN as an encoder model for a whole sentence. So if we want to do sentiment classifications to see whether a piece of text is positive or negative, we can say run an LSTM over it and then use this as a representation of the sentence to work out whether it's positive or negative piece of text. And well, the simplest way of doing that is to use the final hidden state, because after all, that final hidden state is the hidden state you've gotten from having seen the entire sentence, and use that and then have a sort of a classification layer, a logistic regression on top of that to give you positive or negative. In practice, though, people have found it's often better to use every hidden state and take some kind of mean or element-wise max and feed that in as the sentence encoding. You can also use RNNs for lots of other purposes where you're using it to generate text based on other information. So if you want to do speech recognition or summarization or machine translation that we'll come to later, you can have an input source which you'll use to condition your network, and then you'll generate the speech recognition or the machine translation, as we'll see later. And so we refer to those as conditional language models, because rather than just generating text starting from nothing from a start token, we're generating it conditioned on some source of information. One other idea on what normally happens when people use these, I suggested that we could sort of do this averaging at each position. If you think of about these hidden state representations, these hidden state representations, that representation isn't only about the word terribly, it has some information about what came before it. The movie was terribly, but it has no information about what comes after it. And well, you might think you'd like to have a representation of terribly that knows what came before it, but also what came after it. And so people sort of came up with the next obvious idea to deal with that, which was to build a bidirectional LSTM. So you ran a forward LSTM, and then you start another LSTM that's shown in that sort of greenish teal, and you ran it backwards. And so then you had a forwards and backwards vector at each position, and you just concatenated them both, and then you had a two-sided context for a representation of word meaning. And so these networks were pretty widely used. So we were sort of running a forward RNN, a backward RNN, and concatenating the states together. And those were then sort of commonly sort of written like this to suggest that in a compact way you're running a bidirectional RNN. These were very popular for language analysis. They weren't workable if you were wanting to generate text, but you were using them in a lot of places as a representation. But more recently, transformer models have normally taken over from that. One more idea, which we'll see for machine translation, is RNNs are sort of deep in the sense that they unroll over many time steps. But up until now, they've only been shallow RNNs in the sense that we just had one hidden state. But you can also make them deep by having multiple layers of hidden states, what is also commonly called stacked RNNs. So you'd have several layers of RNNs built above each other. And you might wonder, does this really do anything? Are they just big vectors above the words? But precisely because you have sort of this extra neural network layer between here and here, you get exactly the same power advantage you get otherwise with neural networks, that you can do successive layers of feature extraction, and so you get more power out of your neural network. To some extent, what people, to some extent, what people found with RNNs in those days is that having multiple layers definitely helps, but unlike what was happening in those days with other kinds of neural networks for vision, etc., people still use relatively shallow RNNs. So, you always got a lot of gains by having 2 layers rather than 1, but commonly it started to be more iffy whether you got extra value from 3 or 4 layers. So commonly people were running 2 or 3 layer LSTMs, and that's what people were using. But that's completely changed around in the world of transformers, where nowadays people are building very deep transformer networks for doing language understanding. Okay, but I should skip ahead and say a few words before time runs out about machine translation. So machine translation is one of the key natural language processing tasks where we're translating words from sentences in one language to sentences in another language. So we're starting off with a sentence in some language here, French, and what we want to do is output it in a different language, here, English. So that machine translation was actually where NLP started, right? So in the early 50s, there wasn't artificial intelligence yet. There wasn't a field of NLP yet, but people started to work on machine translation. And the story of why people started to work on machine translation was essentially, computers were first developed during the Second World War. And during the Second World War, computers were used for 2 things. One of them was calculating artillery tables to sort of work out what angle to put your gun on to get it to land in the right place. Not very relevant to what we're doing. But the other thing that computers were used for was code breaking. After the Second World War, it moved very quickly into the Cold War, and there were, concerns on both sides, of keeping up with the science that was being developed on both sides. And people had the idea of, maybe we could think of translation between languages as like code breaking. And that thought occurred to important, relevant people in science funding agencies, and actually lots and lots of funding was poured into this idea of, can we use computers to do machine translation between languages? And, at the time in the 50s, after some initial very impressive looking cooked demos, it was sort of basically a complete flop. And the reason, there are lots of reasons why it was a complete flop. One was people knew almost nothing about the structure of human languages. I mean, in particular, when I was mentioning the other day the Chomsky hierarchy, right, and knowing about sort of context-free languages, right? The Chomsky hierarchy even hadn't been invented yet, right? Sort of formal properties of languages hadn't really been explored. But also, the computers that people had in the 1950s, right? The amount of computing power or memory or anything like this that those computers had in those days was laughable, right? These days, the little power brick for your laptop has more computing power inside it than the big mainframe computers that they used to be using in those days. So basically, people were only able to build very simple lexicons and rule-based substitution rules, and nothing like the complexity of human languages, which only gradually people began to understand. But machine translation started to become more alive in the 1990s and 2000s decades once people started to build empirical models over lots of data, and the approach then was called statistical machine translation. And so when Google Translate was first introduced to the world, it was sort of the big unveiling to the world of statistical phrase-based machine translation systems, where what you were doing was you were collecting a large amount of parallel data, words that are being translated from one word to another. And, not for all languages, but for quite a few languages, there are quite a few sources of parallel data. So the European Union generates a huge amount of parallel data among European languages. There are places like Hong Kong where you get English Chinese, if a certain dialect of Chinese, parallel data. The UN generates a lot of parallel data. So getting sources of parallel data and trying to build models. And so the way it was done was based on that model, we're going to try and learn a probability model for translation. So this the probability of a translation given a source sentence. And the way it was done at that time was breaking it down using Bayes' rule into two sub-problems. So the probability of the translation given the source is going to be the inverted probability of the source given the translation times the probability of the translation. And you could think that this makes it no simpler because you've just, reversed the order of X and Y. But the reason why it made it simpler and people were able to make progress was the translation model was treated as a very simple model as to how words tended to get translated to words in the other language, and it didn't need to know anything about, word order, grammar, structure of the other language. And then all of that was being handled by just this probability of Y, which was a pure language model, as we've talked about before. So you could have a simple translation model, which just sort of said, if you see the word homme in French, you might want to translate it as man or person or put some probabilities on that. And then most of the cleverness was in the language model, which was telling you what would be a good sentence in the target language. Okay, and so that was important because, translations get pretty complicated, right? So you not only have to know how to translate words, and those translations of words vary in context, but you get a lot of reordering of words in sentences. I'm not going to be able to spend a lot of time on this, but here for a while was my favorite example machine translation sentence. This is actually a translated sentence, so the original comes from the book Guns, Germs and Steel, if you're familiar with that. But it was that book by Jared Diamond. But this book was translated into Chinese. So here's a sentence from the book in Chinese. And, I guess in the 2000s decade, I was involved in building statistical machine translation systems, and I guess there was a MT evaluation that we did where our system did terribly on this sentence, and I tried it out on Google Translate, and it also did terribly in this sentence. So what the sentence should say is, in 1519, 600 Spaniards landed in Mexico to conquer the Aztec Empire with a population of a few million. They lost 2/3 of their soldiers in the initial clash. So here's what Google Translate said in 2009. 1519, 600 Spaniards landed in Mexico, millions of people to conquer the Aztec Empire. The first 2/3 of soldiers against their loss. Now it's partly bad because the word choices and the translations aren't very good, but it's especially bad because it's just not actually able to capture and use the modification relationships of the sentence. So, here's the part of the Chinese that's saying the Aztec Empire, and over there in orange is the few million people. And in Chinese, there's this explicit little character here, dearth, which is saying that stuff in orange modifies this stuff in green, which is what it's meant to be in the correct translation of Aztec Empire with a population of a few million. But Google Translate completely fails on that, and suddenly it's the millions of people who are going to be conquering the Aztec Empire. And that's sort of in this way the worst thing that's happening here. Though the 1519 600 isn't exactly a very good translation, and the first 2/3 of soldiers against their loss isn't very good either. But so for a while I used to sort of update this and see what happened. In 2013, it almost seemed like progress had been made, but by 2015, it had gone downhill back to how it was before. So it just seemed like they got lucky in 2013 rather than the systems were working any better. And indeed, this sort of seemed to be the problem. Although some kind of progress had been made in machine translation, these systems just sort of never really worked all that great. And so that led to this amazing breakthrough in 2014, where we then moved to neural machine translation, and neural machine translation was much better. So what did we do in neural machine translation? So we built a neural machine translation system as a single end-to-end neural network. And that's been a powerful idea in neural network systems in general, including in NLP. If we can just have a single big system and put a loss function at the end of it, and then we can backpropagate errors right back down through the system, it means we're sort of aligning all of our learning for the final task we want to do, and that's been very effective, whereas earlier models couldn't do that. So we built it with a sequence-to-sequence model. So that sounds like our LSTMs, but it's meaning that we're going to have two of them, one of them to encode the sentence, the source sentence, and one to produce the target sentence. So that's what we're building. So for the source sentence, we're taking, here it says RNN, but let's just think LSTM because that's what we're going to use in practice. It's much better. And so we're going to chunk through it, encoding what we've read using an RNN. So this RNN isn't going to output anything, right? We're just building up a hidden state that knows what's in the source sentence. So we get an encoding of the source sentence, and we're going to use that final hidden state to condition the decoder RNN, which is going to then generate the translation. So for the decoder RNN, it's also an LSTM, but it's going to be an LSTM with different parameters. So we're going to be learning one LSTM with source encoding parameters, and then for the different language, we're learning a different LSTM that'll know about the target language. And so we give it start and say, well, feed in your what you've encoded from the encoder RNN as your starting point. And then we're going to be, that'll be counted as the previous hidden state you're feeding into your LSTM. And then we're going to generate the first word of the translation, and we'll then copy that translated word down using this as a generative model as I did last time, and we start translating through, he hit me with a pie. Okay, so that sort of makes sense as the model? Yeah, okay. Okay, there's some notes, sorry. Yeah, sorry. What I was going to say, yeah, so the little pink note here. So what I was showing you is the picture of using it at sort of runtime. At runtime, we're going to encode the source, and then generate the words of the translation. At training time, we're going to have parallel text. We're going to have sentences and their translations. We're going to run with the same architecture, but as before then, for the decoder network, we're going to try and predict each word and then say what probability did you assign to the actual next word, and that will give us a loss. And we'll be calculating the losses at each position, working out the average loss, working out the gradients, back propagating them through the entire network, both the decoder RNN and the encoder RNN networks, and updating all the parameters of our model. And that's the sense in which it's being trained end to end. Okay, so this is sort of our general notion of an encoder-decoder model, which is a very general thing that we use in all kinds of places, right? That we have one network that encodes something, which produces a representation, which will then feed into another network that we'll use to decode something. And even when we go on to do other things like use transformers rather than LSTMs, we're still commonly going to use these kind of encoder-decoder models, because if we want to do not only machine translation, but other tasks like summarization or text-to-speech or other things like that, we're going to be in this space of using encoder-decoder networks. Yeah.
What is the difference between this encoder-decoder model and just using a deeper neural network with more layers?
Well, a lot. It's sequenced. Right, so it has never been very you're meaning like, why don't you just build on top of the source, right? People have tried that occasionally. It's never been very successful. And I think part of the reason is all of what I was trying to show before about all of the word order changes around a lot between languages. And if you're sort of just trying to build stuff on top of the source sentence, it's very hard to cope with that. In particular, it's not even the case that the length stays the same, right? One of the big ways in which languages vary is what little words that they have, right? So that in English, you're putting in a lot of these auxiliary verbs and articles, whereas it's in Chinese, you don't have any of those. And so you're neither needing to, depending on direction, add a lot of words or subtract a lot of words, which is very hard to do if you're sort of building on top of the source of it. Is it quick?
Yeah, so left side, is that sometimes bidirectional or just like the encoder?
Yeah, so you'd totally think, and it could be that the encoder is bidirectional and that might be better. For the famous original instantiation of this that was done at Google, they actually didn't make it bidirectional, so it was simply taking the final hidden state, but that's absolutely an alternative that you could do. Okay. Yeah, so I'd sort of said it was, okay, usable for lots of things. Okay, yeah, so this is our conditional language model. So we're now kind of directly calculating the probability of y given x, right? That the decoder model is generating language expression as a language model directly conditioned on x. And so we train it with a big parallel corpus. And that's the only case I'm going to talk about today. Recently, there's been sort of some interesting work on unsupervised machine translation, meaning that you've got only a little bit of information about how the languages relate. You don't really have a lot of parallel text, but I'm not going to cover that today. Yeah, so for training it, we have paired sentences. We work out our losses in the predictions at each position, and then we're working out our average loss and back propagating it through in a single system end to end as described. Yeah, so in practice, when people built big machine translation systems, this was one of the places where absolutely it gave value to have multi-layer stacked LSTMs. And so typically people are building a model that was, and you'll be building a model something like this, that's a multi-layer LSTM that's being used to encode and decode. In my 2 minutes remaining, I just want to sort of quickly say, so building these neural machine translation systems was really the first big success of natural language processing deep learning. Now, in this sense, you know, it depends on how you define what parts of language. If you look at the sort of the history of the renaissance of deep learning, the first place where deep learning was highly successful was in speech recognition systems. The second place in which it was highly successful was in object recognition and vision. And then the third place it was highly successful was then building machine translation systems. So, you know, Google had a big statistical machine translation system, and it was only in 2014 that people first built this sort of LSTM deep learning machine translation system, but it was just sort of obviously super good, and it was so super good that in only 2 years it was then deployed as the live system that was being used at Google. But it wasn't only used in Google, that neural machine translation was just so much better than what had come before, that by a couple of years after that, you know, absolutely everybody, both US companies and Chinese companies, Microsoft, Facebook, Tencent, Baidu, everybody was using neural machine translation systems because they are just much better systems. And so this was an amazing success, right? Because statistical machine translation systems like the Google system, that this is something that had been worked on for about a decade. Hundreds of people had worked on it. There were millions of lines of code, lots of hacks built in for particular languages and language pairs. But really a simple, small neural machine translation system was able to work much better. There was an article published about it when it sort of went live in the New York Times that you can find in that link. It's a little bit of a praising piece where you could be a little bit critical, but you know, basically it's sort of talking about how just the difference in quality was so obvious that everyone immediately noticed, even before Google had announced it, of, whoa, suddenly machine translation's gone so much better. Okay, so that's basically today. So for today, you know, we've learned that LSTMs are powerful. If you're doing something with a current neural network, you probably want to use an LSTM. You should know about the idea of clipping your gradients. Bidirectional LSTMs are good when you've got an encoder, but you can't use them to generate new text. And Encoder-decoder neural machine translation systems were a great new technology that advanced the field. Thank you.